All right. Hi, everyone. I'm going to welcome you to Curiosity Machine's webinar, Inspire Problem Solving with the Engineering Design Process. My name is Kat Grime, and I'm the head of online community at Redesign. We are a science education nonprofit that powers Curiosity Machine, which is the tool that we'll be using to talk about the engineering design process today. So this webinar is targeted at educators, which is a term we use really broadly. So teachers, librarians, after-school instructors, really anyone working with young people. We're excited to have you joining us. Also, I should just say we really want Curiosity Machine and the engineering design process to feel accessible to everyone. So we believe you don't need a STEM background to do this work, and you don't need STEM expertise to be a great facilitator of design challenges. So just keep that in mind. If any of this feels overwhelming, just remember you don't have to have all of the answers, and we're here to provide support. So if you are watching this on Google Plus or logged in with your Google account, you should be able to ask questions throughout. So there should be a sidebar that says, with a blue button that says Ask the Facilitator a Question. So if you have any questions at any time, feel free to type them in there and it will pop up in my window. It's not exactly live, so I'll have to answer them as I see them, but I would love to hear your questions as we go. Okay, so I'm going to switch over to slideshow mode now. I just wanted to say hi with my face before I disappear. So. Okay, so you should see this slide, Inspire Problem Solving with the Engineer Design Process now. Again, my name's Kat. My email address is on this slide if any of your questions don't get answered today. Okay, and here is a question from Lindsay. Hi, Lindsay. So we have started, and there is audio, so you might just be a few seconds behind. If you could just type another question in the box to let me know if it's working, that would be great. Okay. Cool. Okay, so real quick, our agenda for today, we're going to start with an overview of our learning philosophy to give you some context for how we use the engineering design process. And then we'll walk through the steps of the engineering design process and show you how it looks on Curiosity Machine with some screenshots. And then finally, there'll be some resources for taking this with you and ways to implement it at your own site. So this is the Curiosity Machine. This is what it looks like when you come to the home page. Curiosity Machine is a community of scientists, engineers, and children creating together. And through the STEM education model, children are inspired and equipped to create their own inventions with the support of trained and qualified mentors. So the major components of Curiosity Machine, it's a totally free STEM resource, so anyone can go on here and create an account and access everything that's available on the website. We have videos from scientists and engineers in the field that are paired with design challenges that you can build with really simple household materials. So children build the design challenges in real life, then they upload pictures, text, and videos of their challenges to the website, and then our online community of science and engineering mentors can respond to their uploads and help them improve their designs. Oh, and I just saw from Lindsay, thank you that you refreshed the page and now it's working. And that's a note to everyone. If you're finding that your page is frozen, just hit refresh and that should catch you up to the live stream. Okay, this is the model we use. I just want to show you this so you have a sense of where our design challenges are coming from. So we start in partnership with scientists and engineers. And we train them to develop and teach design challenges to underserved families. So scientists and engineers help us create the curriculum of design challenges, and then we test that curriculum with elementary, middle, and high school populations to ensure that all of our challenges are both open-ended and age-blind. And we'll hear more on that in just a minute. So once the curriculum has been tested, we produce high-quality videos of scientists and engineers sharing the research that inspired the design challenge. The video and the design challenge are then published on Curiosity Machine. So any of the design challenges that you see on the website are linked to real research and to a video that gives some context and really brings the concept to life. So then we train parents and educators on how to incorporate our curriculum. And then we also have online mentors that support the children as they develop solutions to design challenges. So you can see in this model that training a small number of scientists and engineers can have impact on a whole lot of students using the Curiosity Machine. So the three qualities that we believe today's children need to become the innovators of tomorrow are curiosity, creativity, and persistence. And so we'll talk about each of those just a little bit. So curiosity makes children want to discover and explore. Children learn that like other creative pursuits, science also takes time, patience, and perseverance. It requires curiosity to ask questions about the world around us and to want to understand how things in the world work. And we really want to instill a lifelong disposition of curiosity in young people. Right. Second, creativity. We want children to see science as a creative process. So when I recently asked a room of high school students if they thought art was creative and asked them to raise their hands, and music or drawing, lots of hands go up. Then I asked about science, and you see way less hands, and that's the perception that we want to shift. So in science, creativity is really important because it fosters independent thinking and adaptive problem solving. A creative child will be able to get beyond the first solution to a problem or the obvious answer or copying another design that they've seen. And instead, they'll be able to combine and generate new possibilities and find innovative answers to the problems put in front of them. And then finally, persistence. And when we talk about persistence, it's really about students having the ability to work through challenges. So things aren't going to work the first time you build them, more often than not. So think about the first time you rode a bike or maybe tried to like bake a loaf of bread. Like probably it wasn't perfect the first time. So the creative process and the engineering design process, as we'll see in a few minutes, results in many failures. And a persistent child will be able to deal constructively with these failures and adversity and continue on toward their goal instead of giving up out of frustration. So we think to develop these traits, students need many, many opportunities to practice and many hours of practice. They need a safe space to try things and to fail. They need mentors to look to as role models. And they need the guidance and support from parents and educators like you. And so we think that Curiosity Machine offers students a framework for developing these traits through our open-ended design challenges. So on Curiosity Machine, these design challenges, we think that children learn and practice the traits we mentioned by solving problems through building. And our challenges focus on physics and engineering. So they're based on actual science and engineering work, like we mentioned before. And they are doable with simple, low-cost materials that you can find like at the grocery store or the hardware store. We want them to be really accessible. Design challenges are open-ended, which means there are multiple solutions to the challenge, so there's not one right answer. They have low floors and high ceilings, which means they're easy to start. They're accessible to children as young as maybe kindergarten with like parent involvement. But they are also able to make a lot more complex. So they invite everyone to keep building and to develop more complex designs and solutions. So you could have the same challenge with a kindergartner as you could have with, say, a sophomore in high school, and their solutions might look really different, but the same open-ended prompt can lead to both of these. Oh, great. Okay. So just to give a shout out to this question, because I know it'll highlight the questions when I respond to them. Lindsay asked if the scientists' videos are available on YouTube, and Andrew, thank you, answered that they're all available on our Curiosity Machine channel, which is great. And he sent the link to that. I will also send that out in a follow-up email after the webinar. Okay. Okay, so finally, engineering design process. So I just want to do a quick check-in. If anybody has any questions about what you've heard so far, we've answered a couple, but please keep typing them in. I'm happy to be interrupted as we go. Okay, so at the core of our model and of Curiosity Machines design is the engineering design process. So this process is a series of steps that engineers follow to invent new solutions to complex problems. And we take students through it in each one of our design challenges every time we build something. So a couple of things we think the engineering design process does and why we like to use it. It promotes persistence. So you see this build, test, and redesign loop at the bottom of the process. This lets children know that when they make something that doesn't work, they're doing engineering right. So we really like this redesign iteration portion of the process. Second, it demonstrates that it's more important to find their own solution to a problem than to find the correct solution. So the engineering design process is a really good way to encourage students to test out their own ideas to find out whether they'll work, rather than encouraging them away from an idea that you think won't work. And Zan just asked if we could have access to the PowerPoint. I will send this out after the webinar. I don't think that I can get it to you right now because I can't send you a link. But yes, I will send it out afterwards. Okay, so engineering design process promotes persistence, demonstrates that you want to find your solution and not a correct solution, and we also think that it is widely applicable. So you can use this to solve any of our design challenges, but we also think that it's useful as a problem-solving tool for anything in life, in science, or problems elsewhere. All right, so we're going to walk through each of these steps in a little more detail and look at how they're used with design challenges on Curiosity Machine. Okay, so first off, inspiration. So we like to start by sparking students' interest in defining the problem that they're trying to solve. So when you click on any design challenge on Curiosity Machine, you're going to come first to the inspiration page. So this is a screenshot right here from Curiosity Machine, and you can see across the top of the page the engineering design process is running right across there, and it looks a little bit different, but you can see it's the same: inspiration, plan, build, test, redesign, and reflect. And you'll also notice that inspiration is highlighted, and that's because that's the page that we're on, and as we work through it, it will highlight each of the steps so you know where you are as you're working through your design challenge. So every challenge begins with a video of a scientist or engineer introducing their research. So for example, a challenge might look like build a mighty machine is one of our design challenges. And the prompt is build a mighty machine that jumps up, sideways, or flips over. The whole structure should jump in the air. And you can see this is a pretty broad prompt. You can imagine that there might be many different solutions to this. Really the only constraint is that the machine jumps in some way and that the whole structure goes by itself without you lifting it up. So two other things that you'll see on the inspiration page is the inspiration gallery. And that's going to let you see submissions from other students to get ideas. And then the big thing you'll see on the front of the page is the scientist video. And I can't show you a scientist video right now because we're streaming and it will be way too slow. But just to give you a sense of what our videos include in them, we typically show our scientist or engineer who we're interviewing doing research sort of in their own setting. You'll also see scientific concepts illustrated. So you can see in the bottom left corner that is a picture of a bow showing how elastic energy gets stored when you pull it back. And then you can see that applied to the research on the right. So I should say real quick that the scientist in the picture in the upper left is Sheila Patek, and she does her work on very, very fast movements of small animals like mantis shrimp and ants. So that bottom right corner is showing so the illustration on the left being applied to mantis shrimp, and then at the top is also application showing a trapjaw ant that can jump 20 times its body length, which is pretty incredible. Yeah, so the videos introduce students to the work of a real scientist or engineer. It gives them context for how the design challenge fits in the real world, but it also shows a model for what these professionals do, and maybe gives them some insight into a world that they haven't been exposed to before. Okay, so the second step in the engineering design process is developing a plan. So this is a screenshot from the plan phase on Curiosity Machine. You can see that highlighted plan box, so we've moved over one step. And we encourage planning as an important part of the process because it's a great place to explore multiple possibilities for approaching the design challenge to really reinforce its open-ended nature. So sketching out various solutions helps children really think through the parts of their design and maybe where they're going to get caught up or have trouble. And you can make the decision for yourself if you want to have students plan with materials in hand or if you want them to plan first and then grab materials. It's definitely different for different groups. But you will see at the bottom right of this page in the suggested list of materials. So you'll note they're all really simple. I think this is for a bird challenge. Yeah, but also you'll see this button that says Edit Materials at the bottom. And this is really intentional. We want users to be able to go in and change any of the materials that they're using. These are very much suggested, and you can replace any of them as you see fit. Cool. And I just want to highlight that Andrew, who helps with our mentors on Curiosity Machine, is doing an awesome job of hacking the question and answer to leave some side. So please make sure you check those out. He just put a shout out to that Mighty Machines video, which is really great, and you should check it out when we are done. Okay, the other things you'll see on this plan page are prompts to post your plan. So on the left over here, you see the video, the photo, and the writing tool. And this is where students can really start to interact with the website. So once they have their plan, they take a video describing it, or take a picture of their drawing, or write a description of it, and post it to the site. And this is an example of what a page would look like with a submission from a student. So a really nice feature of Curiosity Machine is that anytime you post to the different sections, they're stored. We can't scroll down on this because it's a screenshot, but you would be able to see everything else that you've posted. So when it's possible, and when people have the technology available to do this, it's nice to think about it as a notebook that goes alongside the physical building and designing work that students are doing. So it becomes kind of like a portfolio where they're documenting their process and their progress through the design challenge. Sharing their plan also allows mentors to give individualized feedback and to ensure that children understand the challenge prompt. So anytime you submit, our mentors can claim a student project and give feedback, answer questions, encourage them to the next step, whatever comes next. So hold on, I see a question. So Lindsay asked, when you replace materials in the list, let me go back to here. Does the title change away from suggested materials? That is a good question, and I am not actually sure about that. I think that it stays as suggested list of materials, but I can look into that. Or you could go ahead and test it out yourself and see what happens. Okay. Okay, so the third step is the build, test, and redesign loop, and this is where students will spend most of their time on a project. So again, you see that we've moved along to the next part of the engineering design process. We're in build, test, and redesign. And this is where students really get to study their problem and learn from their mistakes and try again. So as they're building and testing, they're making observations, they're tweaking things, and they're repeating this as many times as needed. We really want students to be testing as much as possible. So that could mean making a really small adjustment, or it could mean going to an official testing station to see if your design achieves the goal. So that the build, test, redesign is kind of a fluid, ongoing process for all of the building. You'll also see on here prompts to document your design and upload, very similar to the plan page. And this next page shows an example of what an upload might look like. So this is a video from a student where you can see he's showing, okay, my CAM mechanism works, but as you can see, the vertical straw keeps on going side to side. Like, any way I could stop that? So it's really great when students are uploading if they include sort of what's going well, what they have questions about, and then our mentors are able to respond and help with their specific problem. The build, test, redesign loop is a really nice place to talk about the relationship between persistence and failure. So this is the part in the building process where students are really trying out the design that they conceptualized, and as we said before, more often than not, it's not going to work right away. So one of our core values is to develop persistence in students. So persistence is inextricably, though, linked to failure. So being able to persist means being not afraid to fail. And to develop this courage to fail requires lowering the stakes of failure. So failure is kind of a big, scary word, but it can mean something as simple as that vertical straw in the last slide that kept moving side to side, just something not working in your design. Or it could be something bigger, like my entire suspension bridge crumbled right in front of me when I tried to test it. So we really need to support students in working through these challenges. So the expectation and stakes of failure are set by the type of activity as well as the feedback that we give to students about the activity as they go. So one of the things I like to do at the start of a session is really set the expectation that we are not going to get this right the first time, and that's going to be okay. Our design challenges are really constructed to be challenging, so we don't believe a student should be able to complete the activity on their first attempt. But through careful reflection and redesigning and support of mentors, they should be successful by the 4th or 5th try. I'm going to skip through a couple of these. So we said before we wanted students to try out their own ideas. There's never one correct solution. And then, yeah, having an initial failure, realizing that that failure is okay, and then achieving eventual success leads to students developing persistence. So our mentors are trained to support that component in the middle, especially, letting students know that failure is okay and to be comfortable redesigning and redoing their initial attempts at a problem. So one way to look at their job as a mentor, in addition to giving support around science concepts, is to promote and encourage failure. And I see a question from Susan that I'm going to get to in just one second, but just to go through the reflect stage really quickly, once students have worked through the build, test, redesign loop, we move them on to reflect. So this is actually one phase of the process on the website that is locked until students have completed their design challenge. But yeah, so this is how they wrap up their project, the answer a reflect question, and you can also pick a photo and publish it to the inspiration gallery so that when other users come to the site, they will be able to see it. Let's move the small groups to begin. Okay, so this is a question from Susan, who works with elementary school students, and asking if we recommend working with individual, pairs, or small groups to begin this type of activity. Yeah, so I have definitely seen this work in pairs and small groups. I think actually a good question to ask is what your technology situation is like, because if you're trying to take advantage of the website but you have less technology than students in the room, I think working in groups can be a really effective way to make sure that everyone is getting challenges up on the website and getting feedback. But I've also seen working at kind of pairing students but having them build their own design, because a really important part of it is the hands-on part of building. So for some of the smaller challenges, I think it's nice for students to sort of have their own materials in front of them. So you can play with that as it makes sense. Okay, so we just have a few minutes left, so I'm going to jump ahead to this resources page. I'm going to send all of these out to you after the webinar. The place where we have a lot of our educator resources is on the curiositymachine.com/educator page. And really good to look at would be the Curiosity Kit, which is designed to support facilitators, especially in like out of school time spaces, so like after school or libraries, but you could really use it for any setting. And also great is the suggested design challenges, which is a flyer we have that puts some series of design challenges together that you could use. So I'm going to let this page sit for a minute, and I know we only have a couple of minutes left, so I will leave my contact information in the follow-up email so you can reach out with any questions. But if anybody has any questions, this would be a great time to ask them. Okay. I don't see any popping up right now, so I will just say that we'd love for you to go explore yourself at curiositymachine.org and try out an engineering design challenge with youth, and also to let us know how it goes. We love to hear from our partners who are using the website. And to connect with us, you can like us on Facebook or send us something on Twitter. You can also just email me directly. Again, it's kat@iridescentlearning.org. And I'm happy to answer any questions. Let's see. Yes. Great. We have a question from Lindsay. All right, so Lindsay asks, is there any plan to create more design challenge series lists? She wants to use them for a club. That's awesome. So if you go to the flyer, and I will send this in my email, there's actually like 5 or 6 series that we've created so far. And I've seen these are really popular so far, so I'm sure that there will be more on the way. But there definitely is a solid bank of them to get you started. I also think another way to sort of progress through the challenges on the website, they're categorized by different types of engineering. So there's like aerospace or mechanical engineering or biomimicry, and you could spend some time going through all of the different challenges under a particular theme. Okay. Great, so I think I got to all of the questions. And we're right at 2:29, so just about time to wrap up. Again, if you have any questions, please email me. Thank you so much for joining us today, and I will send a follow-up email with both the slides and the resources that I mentioned, and any other answers that you might need. All right. Okay, thanks again.